Okay, now we are looking at preparation of alkanes. Preparation of alkanes. There are four ways of preparation of alkanes that we are going to look at. Of course, without taking into consideration the natural sources. The first one we are saying is hydrogenation of alkenes and alkynes. Like the word hydrogenation. Hydrogenation is addition of hydrogen atoms to a compound. Of course, this one is only possible in presence of catalyst. And we are saying we can either use nickel at 150 degrees, we can use platinum or palladium at room temperature. I.e., what we are saying is, for example, if you have an alkene of a general formula CN H2N, right? We are saying if I add a hydrogen in presence of, if I use nickel, then I must use 150 degrees Celsius. And in that case, I'm going to add hydrogen here and it will become CnH2n plus 2. CH2n plus 2. And in that case, an example we have, it may be an alkene. That is maybe CH2 double bond CH2 in presence of hydrogen, in presence of nickel catalyst at 150 degrees Celsius. I'm just going to add one hydrogen here and one hydrogen there, and it shall become CH3, CH3, of course, forming a saturated compound. That means the hydrogen atoms are gone. The double bond. If it's a triple bond, CH triple bond, CH, in this case maybe I can choose to use platinum, but we have said when we use platinum, stroke PT, we are going to use room temperature, room temperature. RT means room temperature. In that case, I need twice the number of hydrogen atoms as for alkenes, because now here I have to replace 2 bonds. So I'm just going to put a 2 here, and that one will be still CH3, CH3. Therefore, we can change alkenes and alkynes to alkanes by addition of hydrogen in presence of catalyst. If it is nickel, at 150 degrees. If it is platinum or palladium is palladium, while platinum is PT. Of course, nickel is Ni. Yeah, nickel is Ni. Our second method, we are calling it decarboxylation. Decarboxylation is simply the removal of a carboxylic functional group from a compound. In that case, we are saying we must heat in presence of soda lime. Soda lime is basically sodium hydroxide, solid, and calcium oxide. A mixture of sodium hydroxide and calcium oxide is what we call soda lime. When this happens, the carboxylic group is cut off from the compound. I think we are saying that we can have a general carboxylic group as RCOO, but in that case we are saying we have to use a sodium salt of a carboxylic group. Maybe ROOC, RCOO, Of course, R in this case, remember we said R can be a CH3, it can be CH3, CH2, it can be as big as possible as long as it is a derivative of an alkane. So in that case, if this happens, in that case I must use soda lime. Which soda lime you have said is sodium hydroxide. This has to be a solid, and then calcium oxide that we must heat. When that happens, then all this carboxyl group is replaced by hydrogen, and therefore we have RH. The resultant compound will have less number of carbonyl atoms because the soda lime takes away the carboxyl group, so the carbon goes along with it. For example, if you have CH3, e.g., you might have CH3, CH2, that is our R, CH3, CH2, then COO, NA, COO, NA. In that case, I am going to add my soda lime, which is actually sodium hydroxide. Sodium hydroxide is a solid also. Sodium hydroxide solid. Stroke calcium oxide still also solid in presence of heat. In presence of heat. In that case, this carboxylic group is going to be chopped off and replaced by hydrogen, and therefore we end up with CH3, which is actually also an alkane. So it depends on the compound that has been given that will determine the method of preparation. So if they had given you a compound as a salt of the carboxylic acid, then you must use soda lime in order to arrive to an alkane. But if they have given you an alkene or an alkyne, then you must add hydrogen in presence of either nickel at 150, palladium or platinum at 120, and at room temperature. Okay, now the third one, we are looking at the hydrolysis of Grignard reagents. Of course, a Grignard reagent is the result of the reaction between the alkyl halide and magnesium in presence of dry ether. Magnesium in presence of dry ether. In that case, for example, we can have RX, and now we are adding plus magnesium in presence of dry what? Dry ether. Or some can just write RX, they say magnesium stroke dry ether on the arm. In that case, this magnesium is going to come and attach itself between the alkyl halide and the magnesium. In that case, we shall form RMGX. And this is what we are called a Grignard reagent. In that case, we are calling it alkyl magnesium halide, where alkyl is the R, then magnesium halide, where in this case the halide is represented by the X, and we are saying in this case, if this Grignard reagent is hydrolyzed in the acidic medium, we are going to arrive to an alkane. In that case, we are saying RMGX, and now we are adding water, but the water must be what? Acidified. The water must be acidified. That's why I'm adding H plus to mean acid. In that case, the magnesium is going to be eliminated, and it's going to be, the magnesium halide is going to be eliminated, and is going to be replaced by a hydrogen. And in that case, we shall form RH. And then now this magnesium and the halide shall take the OH from water, and we shall form MgOH. And a clear example, e.g., still if my R is CH2, I can form my R as CH3. Last time my R was CH3, CH2. This time it can be just CH3X, and I'm saying I am adding magnesium in presence of dry ether. Magnesium in presence of dry ether. We said we are going to form CH3Mg. In this case, let me make XCl. The halide is Cl, so it will be Cl here. It will be Cl there. So that methyl magnesium chloride, I bring it here. CH3Mg Cl. I said in this case we are going to hydrolyze in presence of an acid. In presence of an acid. So this magnesium chloride is going to be replaced by hydrogen atom, and therefore it shall be CH4, and then plus, now this is going to be magnesium hydroxychloride, MgOH, MgOHCl. At the end of the day, what we are interested in is the main product, which is an alkane. If this was CH3, still this would be CH3, Here we will end up with CH3. End up with CH3. Maybe I can illustrate it for some people who might want it. I can illustrate it still. It can be CH3, CH2, Cl. I am adding, in fact, you can even generalize. I am adding magnesium in presence of dry ether. This is my first step. Magnesium in presence of dry ether. My second step, I am adding hydrogen ions in presence of an acid. I am hydrolyzing hydrogen in presence of water. It means I've combined the two steps, and therefore I have avoided the alkyl magnesium halide, and I go directly to an alkane, which in this case I am replacing this Cl with H, and it shall become CH3, CH3. So that is it. Okay. Now we want to look at the last one under preparation of alkanes as the was reaction. In this case, the was reaction, we are going to heat an alkyl halide using metallic sodium, but still we are going to use dry ether. In this case, this formula of preparation, it doubles the number of carbon atoms. For example, if the alkyl halide I'm using is CH3Cl, this is an alkyl halide. Of course, halide is a group 7 element. I'm adding sodium in presence of dry ether. Sodium in presence of dry ether. I'm saying that the number of carbon atoms in the alkane form shall become twice the original compound. Since the first compound had 2 carbon atoms, then the product form this one has 1 carbon atom. It means the product shall have twice, that is 2 carbon atoms, and therefore it shall be CH3. If the compound is, for example, CH3, CH2, Cl, I am adding sodium in presence of dry ether. Sodium in presence of dry ether. I'm going to multiply the carbon atoms by 2, and it shall become, this will be CH3, CH2, but times 2. So it shall be CH3, CH2 times 2. So it shall be again CH2, CH3. So this formula or method, it always gives you a compound, an alkane with even number of carbon atoms, because this method multiplies the carbon atoms in the alkyl halide times 2, giving you an alkane. If the carbon atoms are 3, CH3, CH2, CH2Cl, it can be Cl, it can be Br, depends on which one you are trying to use. Sodium in presence of dry ether, just going to multiply the carbon atoms, and then it shall be CH3, CH2, CH2, and then I multiply by 2, so I will write this in the opposite direction, CH2, CH2, CH3. These ones are so important, especially in the censuses. reactions that we'll be looking at later. We want to look at the physical properties of alkanes. We want to look at the physical properties of alkanes. Of course, since they are in the same homologous series, we had said earlier that for compounds in the same homologous series, as you go down the group, there is an addition of a methylene group, CH2. And because of that, it ends up increasing the molecular mass of the compounds as you go down the group. Also, the increase in the molecular mass, it tends to affect the physical properties. For example, we are saying the boiling and the melting points, they increase with increasing molecular mass. That means as the number of carbon atoms increase in the alkane, also the molecular mass, increases, and therefore the boiling and the melting points increase. But we are saying that the compounds which are branched, if we are comparing the same compound with the molecular mass, the same molecular mass, maybe we are comparing isomers, the branched isomers are more volatile than their companions which are not branched. That the meaning of more volatile means that they can easily boil or they can easily melt. That means they have lower boiling and melting points. And we are saying that the volatility increases with branching. If there is one branch, the volatility increases to a certain level. If the branches are 2 or more, then that means that the volatility becomes extremely high. In that case, we're also saying that alkanes are immiscible in polar solvents. Of course, this comes because of the covalent bonds that are present in the alkanes. The carbon-to-carbon bonds, these ones are covalent. Also, the carbon-to-hydrogen bonds are covalent. That means that alkanes are purely covalent. And covalent compounds do not dissolve in polar solvents like water, but however, they are soluble in non-polar solvents such as chloroform, tetrachloromethane. Of course, the reason here comes because the condition is like dissolves like. Covalent compounds dissolve covalent compounds. Compounds that have polarity, that means they have some ionic character. These ones dissolve in other compounds that have some polarity or some ionic character. So that's why we're saying that they are immiscible in polar solvents, but they are miscible or soluble in polar solvents. For example, when you look at paraffin, paraffin does not dissolve in water, but paraffin can dissolve in petrol. You see that? Also saying that the density of alkanes increases with increase in molecular mass. Of course, this one is very clear in the sense that we know that by formula, density is mass over volume. And of course, mass in that case can become or can be represented as molecular mass. That simply means that density is directly proportional to mass in that case. So the more mass increases, the more the density increases. That is why the first alkanes are gases, and then as you continue down, they become liquids, and they end up becoming waxes.